What's up everyone, welcome back to my channel. So in one of my old videos, I claimed that factorization might not be unique even if we're trying to do prime factorizations or irreducible factorizations, meaning that we're trying to break the expression into factors that are either primes, not necessarily prime numbers, but prime elements based on whatever the content we're talking about, or break it down into irreducible factors. So in that video, we found that prime factorization and irreducible factorizations are not necessarily unique, meaning that we might actually have an expression that if we try to factorize it into one of those two contents, we will end up with different expressions at the end. It might not be necessarily the same as how we usually factor. So in that video, I actually gave an example for each case. For the prime case, that's quite obvious. That's what we really meant by not unique. However, when I use an example in the irreducible factorization case, I thought that I made a correct argument at first because I said linear factor cannot be reduced anymore. But I actually got told that I made a mistake somewhere, and I'm kind of surprised that none of you actually left a comment to me that I made a mistake either. So today we're gonna talk about why that example is invalid and what should we do, or is there any other example that actually makes the argument works. And again, that argument is still valid, that irreducible polymerization, or not polymerization, factorization might not be unique, but of course not for all the cases. Sometimes it's still unique, but sometimes it's not. And we will later on find out a counterexample that shows irreducible factorization might not be unique. Okay, so let's jump back to the incorrect example here. So in that argument, I said we're going to look over the extension ring Z6 joined with X, meaning that now we have all the coefficients of the expressions are in Z6, meaning that we're going to take the integers and divide by 6 and then leave off with the remainder. So we'll end up with 0, 1, 2, 3, 4, and 5 as our coefficients. But then when we say join X, we're now trying to extend it from just those remainders into polynomials with the coefficients that are in those remainders. So for example, again, we can have 3x plus 5, or maybe x squared minus 2x plus 4, but usually we'll again change the minus sign into plus sign by adding copies of 6, because technically we don't have negative in our subring Z6. But either way, we'll be able to convert it back and forth, especially in our calculations or factorization with algebra. It will be easier if we can actually use negative, so that we will be able to use more old tools that we have used, such as taking the difference of squares and so on and so forth. So in that argument, we said that we can have x plus 1 times x plus 2, which is of course equal to x squared plus 3x plus 2. It's actually equal to the right hand side, x plus 4 times x plus 5, which is equal to x squared plus 9x plus 20. And again, you can just try to reduce the 9 by subtracting multiple copies of 6 until it hits one of the numbers that's within 0 to 6, but not in, but 0 to 5 actually. So in that case, we can subtract 6 here to get the linear term 3x, and similarly we can do it for the constant term by subtracting 3 copies of 6, which is 3 times 16, no, 3 times 6, which is 18. So we'll get 20 minus 18 equals 2, which matches the left-hand side here. And we saw that in that video that why the left-hand side is equal to right-hand side now. And we claim that we have different factorizations, different expressions as we try to factorize the same quadratic expression. And in that video, again, I claim that since these 4 terms are linear, meaning that we only have x to the first power as the leading term, it's not factorable or not reducible anymore. So it looks like that the left-hand side and the right-hand side are in different expressions, and then all the factors are irreducible. But here is the truth. In fact, unfortunately, all these 4 terms are actually reducible. How do we show that? Well, here is the deal. When we consider C6 joint the polynomial here, x, the C6 part can be also written as Z2 cross Z3, where both of them are actually not just rings, but they're actually fields. But what does that really mean? It means that these two can actually end up with Z6, or we can say that Z6 is the direct product of the 2 rings here, or the 2 fields here. So in fact, we can consider it as Z2 with x, join x, multiply with Z3, join x. And actually, this is not a good notation here. I'll just use the regular multiple sign, like this. So in this case, we can think an element as a pair, a set. Well, we can actually think an element as a pair of it's actually a pair of 2 components, where each component is following from the extended ring that we have up here. So we can say that the first component will be an element from Z2 join x, and the second component be an element of Z3 join x. So what does that mean? It means that, for example, if we try to look at an element up here such as x plus 1, x plus 1 can be written as x plus 1 here joins x plus 1 here. So it doesn't really look as different from what it is. But if we try to use another example, such as, let's say, x plus 4, then consider x plus 4, the expression itself. If we try to reduce it in mod 2, meaning that we try to rewrite the coefficients in Z2, then x plus 4 is in fact just the same as x itself. And for x plus 4 in Z3 join x, we can reduce the 4 by subtracting 3 so that we get x plus 1. So in fact, if we try to pick an element up here, we can break it into a pair of we can break it into an element that contains 2 components here. So how does that help us? Well, if we try to do this for all of them, we actually get the following. Let's say if we try to do the left-hand side. So the left-hand side is x plus 1 times x plus 2. But if we try to break it into 2 components, for each factor, we have x plus 1, comma, x plus 1 still, which is great, times the second factor, x plus 2. But again, in Z2, 2 is actually congruent to 0, so we'll reduce x plus 2 into x itself, and then comma, we have x plus 2 here. Good. So let's look at the right hand side. If we look at the right hand side, we start off with x plus 4, but x plus 4, if we write it into two components, we will have 4 is reduced down to 0 in z2 and reduced to 1 in z3. So we actually end up with x comma x plus 1. Then we're going to multiply with the second component, which is x plus 5. But again, x plus 5 in z2 will be just x plus 1, as 5 is actually an odd number. Divide by 2, we end up with remainder 1. Similarly, in z3, we will reduce the 5 by subtracting 3, so that we end up with x plus 2. So what does that do? Well, if we look at it as an element with two components for each factor, we can now try to break each factor into two different factors as well. So for example, on the first one, x plus 1 comma x plus 1, we can actually rewrite it as 1 comma x plus 1 times x plus 1 comma 1. And why is this true? Because when we have an element with two components and do the operations, regardless if we're doing regular addition or regular multiplication, we're only doing it component-wise. Meaning, if we try to multiply the two things together, we're only taking the first component and then do the operation, and then we will just take the second components and do the operation separately. So in other words, we can also try to factor out separately as well. So we can consider 1 comma 1 is our multiplicative identity. In other words, it's just the unity. And again, it should be fair, because if we try to put them back together, we'll just end up with 1 in z6 join x anyway, and that is of course clearly an unity. So we can just try to think it that way, so that now we see if we try to factor this out by choosing one of the components b1 and then just reduce the other factor, we'll be able to end up with something like this. For example, if we try to take the first component b1 and then factor out completely for the second component, which is x plus 1, then if we divide this from what we started off, the first component is still going to remain the same because we're just divided by 1, which means we're not changing it. But then for second components, we take since we take everything out as we divide it, we'll end up with 1 as our answer. So we see that each one can actually break it into this way. So let's see what we'll get. First one we have already done, which actually will break it down into the two factors of components. So let's take a look at the second one. If we play the same game, we will now end up with 1 comma x plus 2 as our first factor, because now we're saying that we want to make the first factor into 1 and then bring the second first components be 1 and the second components be whatever we start off. Then if we take this out or factor this out, then by division we will end up with x to be our first component, and then we have x plus 2 divided by x plus 2, which gives us 1 as our second component. Great. So what happened to the right hand side? Well, we can actually do the same thing again. If we try to break the first element or factorize the first element, we will end up with 1 comma x plus 1 times x comma 1. Okay. X comma 1. Good. So if we continue and factor out the second factor, we will get 1 comma x plus 2 times x plus 1 comma 1. So now if we try to compare between the left hand side and the right hand side, we actually see that each side has 4 different elements, and in fact we'll be able to pair them up. We have x comma 1 here and x comma 1 here. Good. We have 1 comma x plus 1 and 1 comma x plus 1 at the beginning. Great. Then we also have x plus 1 comma 1 and x plus 1 comma 1. And finally, we have 1 comma x plus 2 on the left hand side as well as the right hand side. So we see that in fact these factors are actually reducible. They are not irreducible, meaning that we still can break it down into 2 or more factors that are not prime. Or I shouldn't say not prime, not units. So in fact, if we try to rewrite these factors back into Z6 join X, we will actually get the first one is, let's see, we have X is let's see, 3k plus 1, and then here we have X is multiples of 2. So within 6, the only possible way to get it is 4x, and then we have plus 1 here. Well, we have 1 mod 2 and 1 mod 3. That's just going to give us 1 mod 6. Again, it's very easy because there are a couple ways. You can either write out a list and brute force it, or you can just use the Chinese remainder theorem because those 2 are actually relatively prime. 2 and 3 are relatively prime, so that it guarantees that within their LCM, the least common multiples, which is actually the product of M6, there must have a unique value that satisfies the conditions that we have. But anyway, that gives us that the first factor is this, and then the second factor, we can just play the same game again. We have 2k plus 1 for a linear term. We have 2k plus 1, which is also a multiple of 3. So clearly it has to be 3 because it's a multiple of 3 but odd at the same time. So either 0 or 3 is a multiple of 3 anyway. So we can choose quickly. And then we have plus, here is a 1, meaning we have 3k plus 1, which is also an even number. So in that case, it will be 4. Okay, so let's wrap up the other 2. The other 2 is actually going to give us the following. We have 4x plus, here we have multiples of 3 plus 2 plus 1, so it's odd, and then plus 2 mod 3, which is in this case, and the only option is 5, and then times the last term, which gives us 3x plus 1. So in fact, we will be able to break the left hand side and the right hand side into the expression here, so that we actually end up with the unique irreducible factorization for this scenario. And in fact, we just shown that all these linear factors on top, x plus 1, x plus 2, x plus 4, and x plus 5, those 4 linear expressions are reducible, and each one can be written as a product of two of these 4 factors. So Does that mean the argument incorrect? So does that mean that irreducible factorizations are always unique? No. Here is the actual counterexample that shows that y is still not unique. So now we're going to consider the following. We're going to take the integer, join it with the radical of -5 or square root of -5. So you can, of course, just write it as the integer joins I times radical 5. Or radical 5 times I, however you want to write it. So now we're going to consider this this ring here. So in this extended ring, what it really means is if we consider an element in this ring, it must have the following form. It is similar to how we take the integers joined the imaginary unit I itself, which gives us what we call the Gaussian integers, which means that in that case we will have a plus bi, for both a and b are of course in the original ring, which is the integer. So in this case we'll actually have elements looks like this: a plus b times itself I, which is what we're joining with. We're going to put radical -5 or square root of -5, which is what we have inside of the bracket. And of course, such that we have the conditions both a and b are integers. So of course we can get some examples. Some examples would be like, let's say 5 plus 4 times radical -5. This satisfies the condition, so this is actually an element of this ring. Of course, we can have something such as just 27. Well, you might think 27 doesn't have the other term, right? Well, it is fine because b can be any integers, and again 0 is an integer, so we can actually rewrite 27 as 27 plus 0 times radical -5. So we see that 27 is also an element of this. Now, some counterexamples. 3/2 minus 5 radical -5. This is not an element of this ring because the first part, the real part, 3/2 is not an integer anymore, so it doesn't satisfy the condition. Another example that is a little bit tricky to think of is 4 minus I. Why is it not? Well, because here I is actually the imaginary unit, which means we can rewrite it as the following: 4 minus radical -1, but we cannot really rewrite -1 as either part or the real part that contains the integers only. We cannot rewrite radical -1 into the second part, which says integer times radical -5, because again, if we try to take this part and divide it up or factor it out from the second part, we actually will end up with square root of 5 on the denominator. But clearly square root of 5 is an irrational number, so we cannot end up with b as a rational number that satisfies this condition here. So again, this does not work. And of course, something like pi or e are not elements because they are not rational numbers, meaning that they're not integers, so it won't be able to satisfy. Good. With enough examples, now we're going to consider the argument. So our argument is by the following. First, we are going to pick an element in the ring. In this case, we will pick 9 for our argument. And clearly 9 is an element of this ring because 9 is an integer, so it satisfies the condition that we need. Good. So first, we can consider the regular factorization within an integer, and clearly we say that 9 is a perfect square, so 9 is equal to 3 squared, or 3 times 3. And of course 3 times 3 meaning that we have 2 factors but they're just the same copy, 3 is an element of an element of the ring. Again, 3 is an integer. It satisfies the condition that we need. So far so good. Now, here is actually another way of rewriting 9 or factoring out 9, which is, if we consider 9 itself, we can write it as 4 plus 5. And why do we do this? Because when we have 5, we can actually rewrite it as negative of negative 5. So we can rewrite it as 4 minus negative 5, which means now we have 2 perfect square. Well, clearly 4 is a perfect square that we have, which is the same as 2 squared. Now, what happened to negative 5? Don't forget we're actually in the ring, extended ring that actually joining with radical or square root of negative 5, meaning we can rewrite this as square roots of negative y quantity square, where square root of negative 5 is an element of the ring that we're dealing with. So in this case, as we have the difference of 2 squares, we can actually use the formula that we know to factor out. So a squared minus b squared is actually equal to a minus b times a plus b. So in fact, we can factor it out as 2 plus or minus, it doesn't really matter the order. So let's put the minus here. Radical negative 5 times 2 plus radical 5, like this. And of course, each one satisfies the condition of being an element in this ring, because we can just see that radical negative 5 is the same as 1 times radical negative 5. So it means that we set a equal to 2, b equal to 1 for each case, or maybe negative 1 in each case, so that we see that each factor is an element that we want. So here it comes the question. Can 3 reduce it into one of these two? Similar to what we did in the wrong example, because again, we want to show that 3 is irreducible. So this is the key that what we want to do. If we can show that 3 is irreducible, then it means that we won't be able to rewrite 3 itself into one of these two parts. Or we can even claim that 3 is irreducible, meaning 3 cannot be rewritten as a factor of two elements in this form, where neither of them is plus or minus 1, because those two again are just called units. They have inverse. So good. So how do we do it? Well, we can just use contrary argument to show it. So here comes the work. Here is the proof. Suppose, to the contrary, that 3 is reducible. So in this case, we will write that 3 is actually equal to some product of two factors, a plus b square root -5 times c plus d not plus times square root of -5. Okay, so in the end, we want to show that for a, b, or maybe c, d, because they're interchangeable, one of the pairs must end up with 1, 0 or -1, 0. Okay, so how do we do it? Then we're going to multiply it as usual. We have AC plus AD plus BC, everything times square root of -5. So it's just falling out, and then plus the last term, which gives us B times D times the square of square roots, which is cancelled out and just -5. So we will have minus 5BD. Now again, keep in mind we have the condition that A, B, C, and D are all integers because of how we set up in our ring. So in this case, we get the system of equation. AC minus 5BD is equal to 3, where AD plus BC is equal to 0. Good. So if we try to solve this equation, of course, we have given that second equation says AD is equal to -BC. Okay, so suppose that neither of these elements be equal to 0. Okay, then we will be able to bring the division into our equation so that we will be able to do it. And again, why do we assume it that way? Because first, if we assume that, let's say if we set A is equal to 0, then we have the first equation, we end up with -5BD is equal to 3, which is not true because again, we say that B and D are integers. So we see that, of course, 3 is not a multiple of 5. Then there is no solution. Similar argument for C is equal to 0. Now what if B or D are equal to 0? It's possible. So if B is equal to 0, then we end up with AC is equal to 3. And at the same time, we have AD is equal to 0. In order to satisfy this condition, we must have D equal to 0, because if A is equal to 0, there is no solution for its first equation. So this implies that D is equal to 0, A has to be equal to 3, and C is equal to 1, or the other way around, because again, that wouldn't matter. We will just end up with the pair 3 times 3 plus 0, or which is 3, times 1 plus 0, which is 1. Or maybe the other way around, we have 1 times 3. So we see that it's not factorable it's not reducible in that case, because one of the factors is just simply equal to 1, which is the unit. Then if we play the same game for the other argument, for D equals 0, we will end up with the same result. Therefore, now we need to consider our last case, which is neither of them is equal to 0. Assume that A, B, C, and D are not equal to 0. Then we will be able to rewrite the second equation as fraction. So we will get A could be equal to -BC over D. Excellent. So now if we substitute back in to our first equation, we get -BC squared over D minus 5BD is equal to 3. So we can just bring out the negative to the other side and multiply everything by D. to get b c squared plus 5, let's see, b d squared is equal to negative 3d. Good. So now we will say that we are going to consider the following. Suppose that we're going to reduce, we're going to first factor out the b on the left hand side, and then we're going to take the modulus. So what can we do? It means that if we try to do the following, such as left hand side here and the right hand side, as we write the left hand side as a factor of two terms, well, not factor, multiple of two factors, we will get b has to be either be divisible by 3 or be divisible by d. So let's see, if b is divisible by 3 or is a multiple of 3, then we will say that c squared plus 5d squared has to be a factor of d, because now we will say we will have d must be bigger than bigger than or equal to the second factor, so that we will see that b over 3 is an integer that is greater than or equal to 1, and at the same time d over the stuff inside the parentheses has to be the same integer, which is greater than 1. And of course, if that's true, it means that d must be a multiple of it. Then we will have the argument c squared plus 5d squared is actually a factor of d. Now, keep in mind, neither c or d can be equal to 0. So in this case, if we consider the smallest value of the left hand side here, we will get this quantity c squared plus 5d squared has to be greater than or equal to, let's say the smallest value that we can have is 1 and 1 respectively, or negative 1 is fine. But if we choose some other integers, it will just give us a larger value as we square it. So we will end up with 1 plus 5, which is equal to 6. So that means this value is actually greater than 6. Okay, and of course, clearly, we can also have an argument that this value must strictly greater than 5d squared itself. And again, why? Because we have c can never be 0. So if we choose any integers other than 0 and square it, is always a positive value. And therefore, if we try to add a positive value, it must be greater than whatever we started off. And in this case, we can see that this is greater than 5d squared, which is of course strictly greater than d squared itself. And again, that's because d is non-zero. So in this case, it has to be greater than or equal to the modulus of d, or the absolute value of d. And again, the only way to satisfy it is when d is equal to 1, because we take away the option d is equal to 0. And if d is not 1 or negative 1, then we will have the left hand side is strictly greater than the right hand side. Well, it is even true even if d is equal to plus or minus 1, because we still have a strictly greater sign at the beginning anyway. So this means this argument is invalid. Good. So we end up with the last case, and let's erase the board and then we'll bring it up. We now have the last case that 3 does not divide in this, but now we have the other way, which is D is actually going to divide by B. Then we have, or it's actually both ways. So let's see. No, we will do it this way. If B, let's see. If B is a multiple of D, then of course it means that B over D has to be an integer, first of all. But then that also means that if we rewrite this equation by dividing D on both sides, and then we're going to divide everything inside of the brackets or parentheses to the other side, we see that 3 must be a factor of everything inside the parentheses. And again, this argument is based on the fact that B over D is an integer, as we argue, which let's say is k. Then from the equation down below, as we try to cross divide it, we actually end up with -3 over c squared plus 5d squared. And this thing has to be also an integer because this is equal to B over D. Then by multiplying the denominator to the other side, we see that -3 is actually some integer k times everything in the denominator. In other words, 3 must be a multiple of the denominator. Then we will actually quickly check that this argument is invalid because c squared has to be greater than or equal to 1 as c is non-zero. Similarly, d squared has to be greater than or equal to 1 because again d is non-zero, meaning that c squared plus 5d squared has to be greater than or equal to 1 plus 5 times 1, which is equal to 6. But 3 is definitely strictly less than 6, which is less than the left-hand side, which is c squared plus 5d squared. Therefore, this is a contradiction again. How should I write it? It's also a contradiction. Good. So as we check all the cases, we always yield to the contradiction. It means that the argument that we started off at the beginning, or the assumption that we started off, are actually incorrect already. Therefore, as a result, 3 is irreducible. Do you guys remember what we were trying to argue? We were trying to argue that 3 is reducible so that we will be able to rewrite 3 as factor of 2 product of 2 unique product of 2 non-unique unit factors. So we see that 3 times 3 is equal to 9 is equal to 2 plus, radical -5 times 2 minus radical -5. Even though the left-hand side and the right-hand side are different, they will end up with the same results, but 3 itself is irreducible. So in fact, we can also try to we can quickly see that the other 2 factors on the right are also, it doesn't have to be irreducible, but it's definitely not a multiple of 3 either. So we will not be able to break in the right hand side into 3 times something and 3 times something. So we actually end up with the irreducible factorization, might not be unique in some of the situations. And again, that is just follow from the facts that we will not be able to rewrite the factors from on the left hand side into some other thing, and as well as the right hand side that cannot be reduced or break it down into some other things, some other factors either. Okay, so that's the correction that I want to make. Thank you for watching. I'll see you guys in the next video.